All right, let's get into it. Sometimes you hear about a new technology that sounds like it was pulled straight out of a science fiction novel. Well, today's topic is definitely one of those. We're talking about taking nuclear waste and turning it into batteries that could power things for thousands upon thousands of years. It's wild.
Just take a second and really let that sink in. 28,000 years. This one sentence right here, it really just captures the whole kind of mind-bending promise of this tech. And this isn't just some crazy idea on a whiteboard, right? It's a real scientific pursuit that could potentially solve two absolutely massive problems in one go.
So the big question is, how on earth do you even start to turn one of the most hazardous materials we've ever created into a source of clean energy? It sounds impossible. But like a lot of brilliant innovations, it all starts with just looking at the problem from a different angle. Instead of just seeing nuclear waste as this dangerous thing to be buried, what if you saw it as a source of power waiting to be unlocked?
And this really is the heart of it all, isn't it? For decades, the story of nuclear waste has been all about a multi-millennial problem, a dangerous liability we have to spend tons of money on to bury and guard for basically forever. Well, this technology comes along and just completely flips the script. It says, hey, maybe that long-term problem is actually a long-term solution in disguise. So, what's the magic ingredient here? It's a specific radioactive isotope called carbon-14. And where do we get it? Well, it's found in these big graphite blocks from old decommissioned nuclear reactors. Now, this stuff is a real headache to dispose of safely, but it turns out this very same problematic waste has the perfect properties for creating a whole new kind of power. It's a classic case of one person's trash becoming another's treasure. Okay, just to really put the scale of this into perspective, let's look at this. Your smartphone battery, you're lucky to get 2 or 3 years out of it. Your car battery, maybe 5 if everything goes right. But a nuclear diamond battery, we're talking 28,000 years. That's so long that the Great Pyramids of Giza would be more than twice their current age. This isn't just an improvement, it's a totally different way of thinking about energy. All right, so we've got our radioactive source, carbon-14. But how in the world does a diamond, of all things, turn that into electricity? It sounds strange, but the science behind it is actually pretty cool and surprisingly elegant. The process has a fancy name, betavoltaics, but don't let that intimidate you. Think about a regular nuclear power plant. It uses heat to boil water, create steam, and spin turbines. It's a big, complicated mechanical process. Betavoltaics is completely different. It captures tiny particles, in this case they're called beta particles, which are basically just fast-moving electrons, and it converts their energy directly into an electrical current. No heat, no turbines, no moving parts. It's all solid state.
So here's how it works, step by step. First, that carbon-14 at the core of the battery decays and shoots out a beta particle, an electron. Simple enough? Now, as that little particle zips through the diamond structure, it bumps into other electrons and knocks them loose. This creates what physicists call electron-hole pairs. All you really need to know is that it's creating mobile charges. Then, a built-in electric field acts like a little sheepdog, herding those charges and separating them. And that organized flow of charge, well, that's it. That's your electrical current.
And here's the really brilliant part. The diamond is doing 2 crucial jobs at the exact same time. First, it's the semiconductor that's actually converting the energy. But second, because diamond is literally one of the hardest substances we know of, it's also the perfect impenetrable shield. It completely traps and absorbs all the radiation inside. That means the outside of this battery is totally safe to handle. Pretty clever, right? Okay, so we've got the science down. Now for the fun part. What could we actually do with this? Because a battery that lasts for millennia doesn't just make our current gadgets better. Oh no, it opens the door to things that were pretty much impossible before. Yeah, think about all the places where changing a battery is a huge pain, or even flat out impossible. Imagine a medical implant like a pacemaker that you get once and it lasts your entire lifetime and your kids' lifetimes. No more replacement surgeries. Or what about a deep space probe like Voyager that could just keep sending back data not for decades but for centuries? You could drop sensors into the deepest parts of the ocean or even inside a volcano and they just keep working. It's the ultimate set it and forget it power source. Now, I know what you're thinking. This all sounds a little too good to be true, and you're not wrong. It is amazing, but we've got to bring things back down to earth for a minute. This technology is still very much in its early days, and there are some pretty big hurdles to clear before it starts changing the world. And this right here, this is the biggest one. The Achilles heel, if you will, power output. A nuclear diamond battery doesn't give you a jolt of power. It produces a tiny, steady trickle. We're talking microwatts here. To put that in perspective, that is millions of times less powerful than a standard AA battery. So let's be super clear. You are not going to be running your car or charging your phone with one of these, at least not anytime soon. These are strictly for low-power, long-life jobs.
So really, it's a perfect example of a major trade-off. On the pros side, you've got world-changing benefits, right? The absolutely bonkers lifespan and a genuinely brilliant way to deal with some of our nastiest nuclear waste. But on the cons side, the challenges are just as real. You've got that super low power output we just talked about. It's likely going to be really expensive and complicated to make these things. And of course, you've got the whole public perception challenge. Anything with the word nuclear in the name is going to face a tough climb with regulators and the public.
Okay, so even with those hurdles, you just can't get away from how revolutionary the core idea is. So let's just circle back for a second to that incredible timescale, because it really is the main event here.
So why the huge lifespan? It all comes down to this number, 5,730 years. That's the half-life of carbon-14. All that means is that after 5,730 years have passed, the battery will be putting out half the power it started with. Then wait another 5,730 years and it's down to a quarter. This incredibly slow, incredibly predictable decay is what makes it so amazing. It's why I can keep chugging along for 28,000 years and still be useful. We're literally talking about power on a geological timescale. And that kind of leaves us with a pretty wild final thought, doesn't it? We are on the cusp of creating a power source that could easily outlive our entire civilization. It forces you to think on a completely different level, not just about gadgets, but about legacy, about what we build and why. So I'll leave you with this question. If you had a battery that could basically last forever, what would you build with it?